Hello, everybody. I'm Dr. Shafiq, and I would like to welcome all of you in this video session. Today, we'll be discussing about some of the example problems from retaining walls. Okay, so I'm going to show you two example problems. One of them will follow the Rankine's method. The other one will follow the Coulomb's method. Okay, so let me share my screen with you. Okay. So this is example number 1. You can read that one, that determine the factor of safety of the retaining wall shown in figure 1 with respect to overturning, sliding, and bearing capacity failure. Assume the unit weight of concrete is 24 kilonewton per meter cube. Your delta prime is 2/3 of Phi prime and Ca prime is 2/3 of C prime. Okay, so you have two different type of soils here. This one is sand. On the other hand, this one is clay. Okay, this one is basically at the bottom and the left of the wall. The right side is your sand. Okay, now they didn't say anything like which method I have to follow. If they don't tell that one to you, then basically you have the freedom to choose which method you want to use. Okay, so for here, I'm going to use the Rankine's method because this is a little bit easier than the Coulomb's method. Okay, now let's move forward and see how we can solve that problem. So according to Rankine's method, you have to find out this point here, which is A, and then draw a line through A, vertical line, all the way to the surface of the soil. Now, the point here at the surface that intersects with this line is B. Now we assume that for simplicity, that the active force is acting on line AB here, okay? And basically from A, B, and then all the way this wall, that's actually the whole thing will be work as a wall, okay? Now, you can see here that I need to find out the length of AB because my force is working on line AB. So I know from here to here is 5 + 1, 6 meter, and I need to add this one here. But we already know that from here to here is 2 meter, which is equal to this one here. So this distance from here to here has to be 10 degrees, which is 0.35 meter. Okay, so if I want to find out the total height, we usually call that one h prime. That would be 1 + 5 + 0.35. That's actually 3.65 meter. And the force that will work actually 1/3 from the bottom. So this one is 2.12 meter from the bottom. That's the location of the active force working on line AB. Now we have to find out what is our passive force based on Rankine's method, right? So if my phi equal to 34 and alpha equal to 10, then basically from the table 16.3 or equation 16.33, your Ka is 0.2944. I'll ask all of you just go to this table and try to see that you get the same number or not. That will give you the chance to familiar with this table. Okay. Now, one more important thing here, even though this line, the back face is not vertical, but since we are assuming that the active force is working on the line AB, which is vertical, so we assume here that the back face is vertical. Otherwise, you cannot use that table 16.3. So it doesn't matter according to your Rankine's method whether this one is at an angle 75 or 80 or 60. All the time we usually assume that the back face is vertical here. Okay. So once you get your Ka from here, you can just find out your your active force for that wall that's working here. So you can see which is equal to 0.5 Ka gamma H prime square. So we get 106.8 kilonewton per meter length of the wall. Okay. Now while this one is working, if I try to show that one here, then basically you have to draw a line from here to here, which is 2.12, and then draw that line here. So this is the location where your active force will be working. Now, if this is 10 degree, then basically your force will also act 10 degree with the horizontal. And you can see this is basically your PA here. Once you know this force and this angle, then basically you can get the component of force in the horizontal and vertical direction, right? So I'll take the component of that force. This is horizontal and then this is vertical. And if we calculate that one, then basically PH is equal to PA cosine 10, which is 105.2 kilonewton. So this one is 105.2 kilonewton. Now you can see also the vertical component, which is the sine 10, 106.8 sine 10. So this one is basically here 18.6 kilonewton per meter. Okay. So now we know like, hey, what are the forces acting from the part of soil here? Okay. Now let's move forward and try to see the factor of safety against overturning. Okay. So we know that factor of safety against overturning is summation of force, summation of moment, which is trying to resist that overturning, and divided by the summation of moment that's trying to drive the overturning. So if you see here in this figure, if you want to overturn like that, then this one must have to tip at that point here, right? Now, first of all, what we are going to do, we are going to divide this whole area into several regular areas so that we can find out the weight of the structure, because the weight is actually try to prevent the overturning. Okay, so now you can see I have several areas. This is a triangle, this is a rectangle, this is a triangle, this one is a triangle, and this one is also a small triangle there. So these are the area. This is area 1, this is area 2, this is area 3, these are concrete, and this is area 4, which is soil, and area 5, which is also the soil. Okay, so now we can get the volume and multiply that one with the unit weight, and then we can get the weight for each of that segment. Okay, so you can see this is W1, this is W2, this is W3, this is W4, and this is W5. So you can see if I take a moment here, then basically all these 5 weights plus the vertical component of the active force, the total 6 force will try to resist the moment. On the other hand, this force, 105.2 kilonewton, that's actually trying to overturn that, like wall in this direction. Okay, so if we take a moment at point C here, then basically that's the calculation I get. So these are sections 1, 2, 3, 4, 5, And you can see, let's say, for example, for 1, the area is half into 1.5 into 6, and then multiply with the unit weight, which is 24 kilonewton per meter cube. So I get the total weight per feet length of the wall. Okay, so in the other direction, it's just 1 unit length, means like 1 meter. Okay. Similarly, I get like for 2, which is a rectangle. So 0.5 multiplied by 6, that's the volume, and then we multiply with the unit weight, so we get the weight here. Then we try to measure the moment arm from point C. Let's say for W1. So we have to measure from there, and you can see this is W1, this is W2, this is W3, and so on. Okay, so you can see here like the moment arm is 1 because the total from here to here is 1.5, and the centroid of that triangle is 2/3 from the apex, which is actually 1. Okay. Similarly, we can see like for this one, actually from here to here, the midpoint here is 0.25. When you add that one to 1.5, so that would be 1.75. Once you know the weight and the distance from C, then basically we can just multiply the force with the horizon, I mean like the perpendicular distance, and we get the moment. So you can see for 5 different components here, as well as the PV, that's actually causing all these moments here. So the summation of resisting moment is just the sum of all these 6 components, and we get like 1075.5. Okay. At the same time, we can see that, hey, what is the summation of vertical forces, right? Which is actually these 5 weights plus this PV. So we get summation of V equal to 456.9 kilonewton per meter length of the wall. Okay. Now we have to see what are the moment that's trying to drive that way. Okay. So that's the moment for overturning, which is 105.2 multiplied by this distance. So this one is 223.0 kilonewton meter per meter length of the wall. Okay. Now, if you plug that one into this equation here, then you can see this one is just this divided by this. So we got 4.82. So, and our factor of safety, usually 3 is fine. So this is 4.82. So we are fine. Now, if you need to, for design purpose, sometimes you need to get another trial to make, like your wall a little bit smaller and try to see whether this one also follow the factor of safety of at least 3. Okay, but this is more of a analytical problem than a design, because for design you need to trial different sections, and since one of the problems much longer time, so they didn't ask you to design any of the problems in your exercise. Okay, they are just asking to analyze just one section and find out the factor of safety. Okay, now let's move forward to factor of safety against sliding. Okay, so basically your factor of safety against sliding is the force that's try to push this way, and no, sorry, that's the resisting force that's try to, prevent the sliding, which is this plus this, and who is trying to push that way, that's actually this force here. So actually we add this force, and when divide that one with this force, that's basically your factor of safety, against your sliding. Now we have to find out our PP. you can see here, this is the soil properties here, and we know for phi equal to 24, your Kp is 10 square, 45 plus phi by 2, because this side is always kind of straight, doesn't have any angle here. And that actually the case for most of the time. So you can see your Kp is 2.37 for phi prime is 24. And if you plug these values in this equation, actually you get your Pp, which is basically 53.3 kilonewton per meter length of the wall. So that's actually 53.3. Now, in many cases, when you design, you can ignore that Pp. Why? Because many times we see that there might be like some, like erosion because of the water will seep through this, like wall, and some of the water, some of the soil can move from there. So many designers choose not to include that one against the sliding. Anyway, for our purpose, we are going to include that one all the time. Okay. Now, what about the other properties here related to your resistance at the bottom of the wall? So your delta prime is given 2/3 of phi prime, which is actually 16 degree, and your cohesion between the soil and the wall is 2/3 of the cohesion between soil to soil. Okay, so you can see 2/3 of 10, that's basically 6.7 kilonewton per meter square. Now, if you plug all those values here, because we already know everything here, then basically your factor of safety against sliding would be summation of V, which we already got. So 456.9, 10 delta prime, which is 16 degree. This is your B, and this is your CA prime, and this is your PP, divided by PA cosine alpha, which is actually this one here. So if you calculate that one, then basically your factor of safety is almost 2. So if your factor of safety is actually less than 2, in practical life, you might have to redesign your wall section. Okay. Now let's move forward and see what would be your factor of safety against the bearing capacity failure. Okay. Now you can see I changed this diagram a little bit. Rather than showing 6 vertical force, I'm showing that one as a resultant of that 6 force. We already know how much is that from the table. And we are assuming this one is X bar from that point C. And we'll find out that X bar, that why this one is working. Okay, so first of all, if I want to find out my X bar, so this is the formula we are going to use, that the moment for resisting minus the moment for overturning divided by summation of V. So we get 1.87 meter. So the summation of vertical force is actually working from here to here is 1.87. So from here to here is 1.87. But we know this is the center line of that wall. So basically your distance from here to this line, actually your E. So what we do, we draw a line here, and your resultant force for this one and this one is actually working along that line, and the distance from here to here, that's your eccentricity. Okay, so we can calculate that eccentricity is nothing but B by 2 minus your X bar, which is actually 0.13. Okay, so if you just convert that one and try to see, that's actually much less than your B by 6, which is 0.667. If your E is bigger than your B by 6, then basically you might have to redesign again. Okay. Now let's see our case here, because this is your eccentricity in one way, because the wall is always a continuous foundation, right? So the eccentricity is B minus 2E, which is 3.74 meter. And your Q is gamma D, which is 19 into 1. You always have to remember that one. Actually, your DF is not from this side. DF has to be always the lower of the two. So here is your DF. So your DF is actually 19. Now for phi equal to 24, you can go to table 6.2 to find out your NC, NQ, and N gamma, which is very similar to what you learned from chapter 6. Okay. Now there is no shape factors here. All the shape factors are 1 because this is, like a continuous wall. So your depth factors, we are just using this equation here, because most of the cases your df by b would be less than 1. Okay, and since the phi is not 0, so we are going to use this equation, and we get like if qd equal to 1.08, if cd is equal to 1.09, and if gamma d equal to 1. Now we also have to find out the inclination. So you can see this is actually your resultant force. And this one is your psi, which is your inclination angle with the vertical, right? So if I want to find that out, we can use that equation here, that your psi is tan inverse this divided by this. Okay, so we get 13 degree. Once you get this inclination angle, then basically we use the formula for inclination factor, and we get your FCI and QI is equal to 0.73, and F gamma I is equal to 0.21. Now we know the ultimate bearing capacity for the foundation is C prime NC. If CD, FCI, you see that there is no FCS because these are 1, so I just ignored that one from there. And you have to use B prime rather than B because it's a eccentric one, right? So if you plug all those values here, then your QU is equal to 368 kilonewton per meter square. Okay, now if you find out your Q max, because this is eccentric, so that here your pressure would be maximum. So try to find out that pressure, which is summation of vertical forces divided by B into 1 plus 6E by B, and we calculate that one, we get 136.5 kilonewton per meter square. So if we plug these two in the equation, then basically we see our factor of safety is ultimate bearing capacity, which is this one, divided by your Q max, which is this one. So our bearing capacity, factor of safety against bearing capacity is 2.7. Okay, that's the way we try to find out what would be the factor of safety against overturning, sliding, and bearing capacity failure. Okay. Now let's move forward for the second example. So this one is saying that it is required to design a cantilever retaining wall to retain 5-meter high sandy backfill. The consultant suggests the dimensions and soil properties shown in the figure. Check the stability with respect to sliding and the stability with respect to overturning. Okay, assuming the retained soil is in active condition, use Coulomb's earth pressure theory, and delta prime is 24 degrees, which means like Actually, this is 36. So basically, this is 2/3 of phi prime. Okay. The unit weight of the concrete is 24.0 kilonewton per meter cube. So they asked us to do that one in Coulomb's method. So we are going to do that one in Coulomb's method. You always have to remember that if the soil is not sand, then basically you cannot use Coulomb's method. So if they don't even say like, hey, follow Rankine's method and Coulomb's method, but the soil here is, let's say, clay soil, then basically you have the only option to do this problem following Rankine's method. Okay. Now let's see how we can do this problem with Coulomb's method. So for Coulomb's method, for your alpha equal to 10 degree, your phi equal to 34 degree, and delta prime is 2/3, means like 24 degree, then basically you can see your Ka is 0.2633. You can see this one is actually vertical here. So basically, we use this table, which is only applicable for granular soil and vertical backface. Okay, the table 16.6 or equation 16.36 actually is for soil which is sandy, and the backface of the wall is 90 degree. Okay, that's the generalization. That's the simplification from the generalization. That's table 16.6. So once we know our Ka, then we can find out our active force. Okay. So if I use that active force, then we see that that's 87.7 kilonewton per meter. Once we get that one, then we just come here and, oh, one more thing here, the location of that PA is h/3, which is actually 2 meters from the bottom. Once we know that, when we come here, draw a line at the bottom, and then measure 2 meters from there, then draw a line here. So that's the point where your active force is working. Okay. Now, for Coulomb's method, actually you have to draw a perpendicular line to that face. But here your back face is basically vertical. So this is actually the line, like which is perpendicular to this line here. Once you get that perpendicular line, so your PA will be acting here with your delta prime angle. Okay. So basically this is 87.7, and this angle is equal to your delta prime, which is 24 degrees here. Okay, and which is actually at a distance 2 meters from the bottom. Okay, once we know that one, then basically we can dissolve that force into two components, horizontal and vertical components. Okay, so you can see our horizontal component is PA cosine alpha. No, that I actually made a mistake here. This is not alpha, that would be PA cosine delta prime. So that's 87.7 cosine 24 degree. So this is 80.1 kilonewton per meter. Similarly, this one is sine 24. So which is 35.7 kilonewton per meter. Once we know these two components of forces working here, then basically we can just go to find out what would be your factor of safety against overturning and sliding, right? One thing you can see in Coulomb's method, actually the force is directly working on the wall. So there is no section here, which is other than the concrete, okay? So let's move forward and see how we can find out the factor of safety against overturning. Again, your factor of safety of overturning is basically summation of moment which is trying to resist the overturning, and this is which is the moment which is trying to drive the overturning. Okay. Now again, what we do, we have to divide this area into several regular areas so that we can find out the weight and then see what are the moment with respect to this point here that will try to resist the overturning here. So let's divide that one. We can see this is your area 1, this is area 2, and this is your area 3. Okay. Now we also have to take the moment from here, so we have to measure the distance actually from this line here. Okay. So now you can see the table here. I have 3 different sections, 1, 2, and 3. 1, 2, and 3, and then I also have a vertical force, which is the vertical component of the active force here, okay, 35.7. So similar way, like you see, this is the area multiplied by 1 in the other direction, and you multiply that one with the unit weight, so you get the weight of this particular section. So for 1, you can see this is half into this into this. So it's half into 0.5 into 5.5. That's the height from here to here. Because you can see this is 0.5 here and this is 1. So from here to here is actually 5.5. So that's 5.5 multiplied by unit weight of concrete. So you get 33, like kilonewton per meter length of the wall. And you can see the distance from here to here is actually 1.5. And from here to here, because this is 0.5, so that would be like 2/3 of 0.5. So that's why it's 1.5 plus 2/3 of 0.5. That's actually 1.83. Okay, because that 1.5 plus 0.33 is equal to 1.83. So once you multiply 33 with 1.83, that's actually your moment. So you fill that table for other 2 sections as well as the vertical force from the active force that's coming from the soil. So once you do like all these 4 moments, that's actually, you sum that up. So this is like 371.7. That's basically trying to resist the overturning. You also try to remember this one because we are going to use that one for sliding, which is the summation of vertical force is 176.7. But we are not going to use that one right now. So we already know this one is 371.7. So we have to find out the overturning moment here. So which is nothing but 80.1 multiplied by 2. So 160.2 kilonewton per meter length of the wall. So if I plug that value in this equation, which is this divided by this, so actually my factor of safety against overturning is 2.32. Okay. Now let's move forward for sliding. We already know that your factor of safety against sliding is this. Okay, so that's basically, if I show that one here, first of all, we have to calculate our PP. Now you can see for 36 degree here, the same soil here actually. So your Kp would be 10 squared 45 plus P prime by 2, which is 3.852. So your PP is basically 35.6 kilonewton per meter. Okay. So this one is 35.6 kilonewton meter. And we also have like this force here, which is actually this part here. Now we know all those values here. We already calculated that one in our table. We know this is 24. We know like your B, which is actually 4.5, and we know this one actually 0 here. So this part would be basically 0. So we can just plug all those values in this equation here. So you can see this part is 0 here. So this is summation of vertical forces 10, 24 plus your PP divided by your PA cosine alpha, which is 80.1 kilonewton per meter. So your factor of safety against sliding is 1.43, which is a little less, but actually that's what they ask you to find out, okay? In that particular case, they didn't ask you to find out the factor of safety against the bearing capacity failure, but if they ask you to do that, that's basically the same thing what you did for example problem number 1. Okay, so that's basically like the 2 problems here, and if you have any question, please feel free to contact me, and thank you for watching.